And now it's my pleasure to introduce Horst Simon of Lawrence Berkeley National Laboratory, the chair of the June 2020 session for the Top 500, the HPCG, and the Green 500 rankings.
Good morning. This is Horst Simon. I am speaking to you from California, so it's early morning here, and it's a great pleasure to join my top 500 colleagues, Jack Dongarra, Erich Strohmaier, and Martin Moyer, to welcome you to the top 500 session here at Digital ISC 2020. This is the 55th list, and it's of course a remarkable accomplishment to have 55 lists going, and so even COVID-19 will not slow us down. And so I'm very happy to tell everybody who is anxiously waiting about the results that the list is alive and well, and we will move forward in the same way as 54 times before. With this, I'm very pleased to introduce my colleague Erich Strohmaier, who is also at Lawrence Berkeley National Lab, and he will go through a presentation about the winners of the top 500 and then give his traditional analysis, first analysis of the new data that we have. And I would like to invite all of you to submit questions that you might have at the bottom of the stream on YouTube. Jack will collect the questions and then post them to us here at the panel at the end of the session. With this, welcome Erich, and let us hear about top 500 number 55.
Thank you, Horst. Welcome to everybody and good morning from California. It is my pleasure to give some of the highlights about the new top 500 list, which we're publishing today, just during this session, at the end of the session. And even under this current circumstances, everybody here would very much like to be in Frankfurt instead, but so are the times. So with that, I switch to my slides. So the 55th list, as David and Horst already alluded to, we do have indeed some exciting news, and I'm going to tell you the next few minutes about the new top systems in the list, as well as some other things. But before we go to that, we have one thing traditionally, which we unfortunately have to do virtual this year, so it's going to be very different than in the past. Every 6 months, we are handing out some certificates for the top systems in the world, and we want to continue that even in this format. However, there is no time to actually switch to other people and accept awards and things like that. So all I'm going to do for the next few minutes, is name the awardees and give them the recognition that way. So I'm going to show you these awards in roughly that same order. And I like to start backwards this time by the #1 system in Europe. The #1 system in Europe is actually a new system which has not been on the list before. It's called HPC5. It's a power edge system, and it's installed at an industrial customer, which is also very unusual for a top 10 system, at the Italian company NISPA. It achieved about 26 petaflops on the Limpact benchmark and made a very respectable debut in the top 500, and we're going to hear a little more about this. So this is the highest ranked system in the top 500 in Europe. The #3 system overall worldwide is actually a very well-known system, Sierra system at Sandia National Labs, Sierra system in the US, which has been in the past the #2 system, and David and Horst already alluded to, we have a new #1 system, so it slipped from #2 to #1, but it's still one of the very big systems in the US, second biggest system. The #2 system this year became now Summit, which used to be the #1 system for a couple of editions of the list, with just about 148, 149 petaflops on the HPL Limpec benchmark. It's installed in the US as well, in Oak Ridge. Okay, and with that, the new #1 system is actually called the supercomputer Fugaku. It's installed at the Riken Center for Computational Science in Japan, and it achieved a Limpec benchmark performance of 415 petaflops. That is almost 2.8 times faster than the old #1 Summit, so it's a healthy increase over the previous state of the art. And it's an exciting new system with respect to a couple of parameters and a couple of innovations it actually introduces into the market and it represents. That's why we asked Satoshi Matsuoka, the director of Riken, to give a little in-depth presentation about the Fugaku system right after my presentation. I borrowed some of his slides just to give you a little teaser. That's a visual of the system. It's not only impressive in its parameters or in its site, but also the visual is quite appealing, at least in my opinion. Highlights from the architectures: it actually uses an ARM core node developed by Fujitsu, which is one of the first ARM systems on the list, not the first one. We have 4 ARM systems on the list right now. The processor has 48 cores. The system does not use accelerators like GPUs. Instead, the cores themselves have vector units, very wide vector units attached, the SV512, 2 of them per core, and that allows Fugaku to achieve a quite substantial peak performance. For application performance, just as important are the other 2 innovations, the other 2 new features, which is, of course, the hybrid memory cube memory attached to each of the cores, to each of the processors, I must say. And the second thing is the new iteration of the TOFU network, the TOFU-D network, which provides tight integration between all the nodes in the system. If you like to see some more in-depth analysis of the Fugaku system, you see the URL for a report check Dongarra puts together at the bottom of this slide and the next slide. So the system itself has about 158,000 nodes, and if you do the math and multiply everything out, you end up with a peak performance in 64-bit double precision of about 537 petaflops. That's quite impressive, and with 415 petaflops, Fugaku achieved a very high percentage of those peak petaflops actually on the Limpec benchmark. Now, Fugaku is very much geared towards future applications, just as current applications and future applications, data-intensive applications, machine learning applications, and AI. And towards that end, the vector units are constructed in a way that you can run them with half precision at double speed, with quarter precision at quadruple speed, and with an 8th precision, 8-bit integer operations at 8 times the speed of 64-bit floating point operations. With that, Fugaku can actually achieve over an exaflop on the reduced precision, and it actually has done so, as I'm going to tell you in a second. The overall memory bandwidth is very substantial thanks to the hybrid memory cubes, and is unusually high for these days at about 0.4 bytes per floating point, double precision floating point operation. So as I said, the hybrid memory cubes and the TOFU-D network allow those vector units, which are very well understood as a technology, allow the whole system to achieve high efficiencies on applications, not just on the Limpec benchmark. And that's documented by Fugaku also being the new #1 on the HPCG benchmark. It achieved about 13.4 petaflops, fairly high above the old #1 Summit, and with an efficiency which is also substantially higher than other systems on the list. So HPCG is a benchmark we have been reporting on for a couple of years. There is a new benchmark in the making. Czech is also developing that. That's a benchmark, a variant of HPL, which is geared towards resembling what AI workloads and machine learning workloads are doing. It's called HPL AI. And the Fugaku system is not only one of the first systems we measured, but between the few systems we have measured so far, also the fastest one by far. And on that benchmark, in reduced precision, 16-bit precision, Fugaku actually achieved 1.4 exaflop. So that's non-trivial because to satisfy the requirements of that benchmark, you cannot just compute only in 16-bit. You actually have to make up for the lost precision at the end of the benchmark and gain back the full 64-bit precision in the results. but that penalty was easily overcome by the more than 2 exaflops of peak performance Fugaku has in 16-bit operations. So with that, Fugaku really is heralding in the exaflop, the age of exaflops, sustained exaflops. And it's going to be interesting to see what Fugaku can achieve on other applications. Another project which works together with the top 500 very closely is the Green 500. And we also hand out traditionally an award for the first Green 500 system. This is the award for the #1 in the Green 500 system, also a new system. It's MN Core's server from the Japanese company Preferred Networks, which is installed in Japan. And it achieved also a healthy gain in terms of power efficiency by achieving about 21 gigaflops per kilowatt on the Limpec benchmark. And I'm going to show the details of that in a second. So what I'm going to now, switching to the regular presentation about the top 500, what I'm going to tell you is a little more details about the #1. I already gave you those. We achieved an exaflop on the HPLAI benchmark. I already told you about that. We have in general a renewed top 10. I'm going to show you that in a minute. The Green 500 shows nice progress in terms of power efficiency. I'm going to focus on other developments in this list, which is particularly a low market turnover. And I'm going to compare the research on the commercial markets and how they actually shake out this time. So top 10, I'm starting with the top 5 this time. In yellow, you see the new list, the new systems on that list, while in white, these are systems which have been on the list at least 6 months ago, in some cases for a couple of years. And you see Fugaku is the #1 system. It's about 2.8 times faster than the #2 system. It also has about 2 times 8 the power consumption in the last column, the power consumption of the previous system, previous #1 system, Summit, which overall makes its power efficiency actually about the same between the first 2 systems, Fugaku and Summit. So Japan, a Japanese system built in Japan and installed in Japan, is now again the #1 system. It's the 6th Japanese system in the 27 years of the list, which has made the #1 position, followed by 2 systems in the US, which have been #1 and #2 for a couple of editions of the list, and then followed by 2 systems built and manufactured and installed in China, and Chinese systems, which also have been #1. So the list of the 5 systems is actually all #1 systems. Now, for the full top 10, I told you there is actually more news, and indeed there are 3 more new systems, positions 5, 6, and 9 on the top 500. The position 6 is the Dell system installed in any SPA, which I already mentioned because it's the fastest system in Europe. It's the first system in Italy. And curiously enough, we actually have a second system from Italy in the top 10 at position #9, which is the Marconi 100 system, which is an IBM-built system. The other newcomer at position #7 is also worth mentioning. It's a system built by NVIDIA. It's currently actually installed at NVIDIA. It's clearly built with the idea of machine learning as well, not just Fugaku, but it is a much more traditional architecture in that way that it's built based on AMD chips, 64-core chips, together with NVIDIA accelerators. So we have 4 new systems in the top 10. That's very nice because the last 2 years we had maybe once we had two new systems, but we had overall very little turnover. But overall, the turnover at the top looks fine this time. We have 4 new systems. That's very nice. In terms of HPCG, we also have a couple new entries on the HPCG list. Here again, the top 5 first. Fugaku again, because of its architecture and its high efficiency, was easily able to take the #1 spot in the HPCG benchmark as well. It achieved about 13 petaflops on the HPCG benchmark, and it has an efficiency which is about almost twice of the efficiency of some of the other systems you see in the top 5 or top 10. So that's quite nice. And with respect to the efficiency of the architecture, it actually follows nicely into the footsteps of the previous system at Oracle, which was the K-computer, because K-computer had for a long time the highest efficiency of any system on the HPCG benchmark. So if you look at the at the full top 10 in the HPCG benchmark, you see that the other two of the newcomers are from the top 10 in the top 500, the HPC5 system and the Selene system, NVIDIA Selene system. They're both making the HPCG list as well in very similar positions. I believe we do not have a number for the fourth newcomer in the top 10, so it's not showing up here. So there is overall progress. The performance levels, of course, on the HPCG benchmarks are still much lower than on the HPL benchmarks. So the other list, top 10 list we typically produce and publish is the Green 500. These are the top 10 systems on the Green 500. Green 500 is a different type of listing as the top 500 or the HPCG list. The Green 500 is really a list which focuses on technology and not on necessarily on size of system. That's why the Green 500 always has a much higher turnover. And you see there is 5 new systems in the top 10 of the Green 500. That's more typical for this type of listing. You see that Fugaku is not the number 1. It is actually just off the top 10. It actually should be here. I don't know. I must have made a mistake on this table. Oh, it is there. I'm sorry. It is there. Of course it is there. It's number 9. Very close to Summit, the number 2 system on the list. Has that really means Fugaku as well as Summit have very impressive power efficiencies. But the new number 1 is a newcomer in the space of HPC. It's a system built by Preferred Network in Japan, and it's using a Xeon chip as main CPU, but using its own MN core accelerator for acceleration of the computations. Most of the systems in the top 10 of the Green 500 are typically accelerated with GPUs, the 2 exceptions being the 2 systems from Fujitsu, Fugaku and its prototype at Fujitsu, which do not use external accelerators, so they are different in that respect. Otherwise, all the systems in the top 10 of the Green 500 use accelerators at this point. The step up from Selene and the MN3 system in terms of efficiency is nice, about 10% over the old number 1, but we just above 20 gigaflops per watt now. So that's good news. And otherwise, you see a lot of top 10 systems from the top 10 of the top 500 on the Green 500, on the top 10 of the Green 500. That's a very nice result too. It's not only small systems which show up here, but very big ones too. And that's an observation we have made for many years, is that the HPC community likes to innovate from the top. So a very large system often are the first ones to receive new technology. And that continues to be the case. Looking at the history of the Green 500, you see the different architectures and how they have improved their efficiency over time, with the MN core system not now just being ahead of the Fujitsu ARM-based systems like Fugaku. It's a nice increase, but the more important increase is actually the blue dots at the bottom of this slide, which show you the increase in average power efficiency in the list. And that's a continuous march upwards, even so not quite as steep as the peak efficiency. So going now to the more traditional slides of the top 500, of course, I'm going to show you the development for the whole 55 lists for the 27 years. And you see the near exponential growth of performance on different levels of the top 500. You see at the bottom the sum of all 500 systems, which now exceeded 2.2 exaflops. In red, you see the performance of the number 1 system, which now has 416 petaflops. That's the Fugaku system, a nice step up at the very right end of that red curve. And in orange, you see the performance of the last entry in the top 500. And we are now at 1.3 petaflops, which is a slight increase of about 100 teraflops per system. So in this list, we noticed in the past, and there were inflection points in the curve, in the bottom curve for the last system on the list. We saw an inflection point in 2008, which roughly coincides with the end of the NAR scaling in computing, which impacted the small systems immediately. there was an effect which allowed the large systems to grow inside and compensate for a while. And the very large systems actually stayed on the old growth curve we had seen in the top 500. But in June 2013, that broke down. And both of those curves are now on reduced growth curves. Both of those curves are now on reduced growth on a different exponential growth path. But they seem to continue nicely along that path, at least for now. I alluded to the fact that the list overall has not seen as much turnover as in the past. It doesn't show in this graph due to the tremendous scales on the left-hand side. But if you just look at the plain replacement rate, how many systems fall off the list at the end of the list due to lacking the performance to qualify, we see that this time only 51 systems fell off the November list due to lacking performance. That's the lowest replacement rate we have seen since the project started. There are two reasons, of course, for that are, or presumably are, that one that we have seen for the last 5 years, reduced turnover in general, as people upgrade less frequent and then upgrade to larger systems. An effect of then our scaling breaking down and of progress and chip performance being much slower than it used to be. But the second effect we assume is clearly the impact of the current COVID-19 crisis, that installations have been delayed or even canceled. It's hard for us to tell which one is what. Presumably or hopefully it's only a delay and we might catch up in the future again, but we have to see about that. So we have a record low replacement rate. That, however, has not changed another trend we have seen for the last 10 years, which is an increase accumulation of performance at the top. The list is getting more and more skewed towards the top. Here you see 5 lines, which is the percentage of the first 5 systems, which they contribute to the overall sum of all 500 systems. And in blue, you see the percentage the first system contributes to the list. And with Fugaku contributes just over 18, almost 18.5% of performance of the whole list. With Fugaku, we have actually a new record in terms of size of the number 1 system relative to the average of all 500s. But the number 2 and so on system are actually fairly large too. And in the past, sometimes the percentage they represent sometimes was only achieved by the number 1 system. So being curious of the peaks, about I actually labeled them for once. The very first peak on the left-hand side was the first one of the first Japanese system to be the number 1, the numerical wind tunnel NWT. The second noticeable peak was ASCII Red in Sandia National Labs in the US, which has been the number 1 for a long time. Followed in the early 2000s by the Earth Simulator, second Japanese system in this listing, actually the third one, which was number 1, followed by the Blue GNL system in Livermore, and the K computer in Japan at the same institution, Riken CCS, as now Fugaku is installed, and the immediate predecessor system before the Fugaku system. The other 2 peaks you see there, Tianya 2A and Taiyu Light, are the 2 Chinese systems which became number 1 at some point in the top 500, and now, of course, Fugaku. So that's the top systems, how much they contribute. And with that, I go to more traditional statistics. First one being, where are these systems actually installed? We have seen a trend going on there for the last 5 to 10 years, that more and more systems have been installed in China, made a dramatic increase around 2015, and now the situation has somewhat stabilized, with China clearly being the country which has installed most of the systems in the top 500, followed by the United States and the European countries and Japan. Now, if we slice the current situation, if you look at the current situation distribution, just looking at performance, of course, the situation is a little different, because in performance size, if you look at performance, the size of the machine really matters. We see that the United States is actually still ahead of China in terms of installed performance, but Japan made a big jump up thanks to the Fugaku system, followed by the European countries again. So Japan almost caught up with China. We have to see how that develops in the future. But the United States consistently is still number 1 in terms of installed performance, ahead of China. The other question in terms of geographical distribution we ask ourselves is where these systems are actually built, where are they produced? So if you look at that, we see an even more dramatic change during the last 5 years, that now the majority of systems is clearly built by Chinese companies. And the trend is that they are built by Chinese companies, and there are many of them, not all of them, but many of them are actually installed in China. Situation seems to stabilize over the last 2 years, so we have to watch that. If it reverts or if it stays with more than 50% of the systems being built by China or not. In terms of companies, you see now the Chinese company being the number one. Lenovo has been number one for a couple of editions of the list, followed by the combined HP Gray count, and the second and third Chinese companies, Shugon and Inspur, followed then by other companies like Atos in Europe and Fujitsu in Japan. If you break the same pie down by performance, it's going to change the sizes of the slices quite a bit. I left the ordering of the slices and the coloring the same, but if we go now to performance, you see Lenovo is no longer the number one. It has a sizable fraction, but the number one currently is actually Fujitsu, followed by Lenovo, and very closely behind IBM. And then HP Gray at number 4 in this statistic at this point. So in terms of sizable systems, large systems, distribution is very different from the mass market and the commercial market. And because of that, we noticed that for many years that there was a difference between our statistics in terms of installation numbers and installation sizes. We dug deeper into actually the differentiation, the different features of the research and the commercial market. So I'm going to focus on this a little bit. And the methodology we used for analyzing that is that we have at least 100 systems in the academic and research, government research market, every list, and we have at least 100 commercial systems in every of the lists for the last 27 years. So we just take the top 100 commercial and the top 100 government research and academic, and compare those two top 100s to each other. We did some checking to make sure that the overall trends are actually all fine. They are. The curves, the growth curves over time look very similar to the top 500 itself. So we felt comfortable that we could do this. This just shows you the market slices and the level 100 and level 200 mark for the different segments. And you see we couldn't have done it with 200, so we did it with 100. So where are these systems now actually installed in these two markets? On the left-hand side, you're going to see a couple of slides where on the left-hand side you see a pie which represents the research market. On the right-hand side, you see a pie which represents the commercial market. And you see in terms of where these systems are installed, research market is still dominated by the United States. So even in numbers, there are more systems in the United States at research centers than in China. Actually, Japan and some of the European countries are still ahead of China in terms of research installations. If you look at the installed systems in terms of the commercial market on the right-hand side, the situation is very different. China clearly dominates the commercial market as a consumer. That has been one of the big surprises, how much it really focuses on the commercial market, with very few contenders being left in terms of producers, but also in terms of consumption. Companies outside of China don't install as large a system, or at least we don't know about them. So if we look at this, this is by system count. If you look at the same pies in terms of size of system, performance count, performance share, we see Japan on the left-hand side made a big jump up thanks to Fugaku in the research installations, now ahead of the United States and China behind. And in the commercial market, the situation, China is still dominant, not quite as much as in system counts, but China installs most of the performance in the commercial market, and is followed by the United States and the European companies and countries and Japan. Now, if you go to the companies who produce those systems, we get the following breakdown in terms of number of systems installed. Research market, the leading company still is and has been for quite some while, Cray, especially now combined with HPE. So the first two slices actually is one company, HPE. So that is a 1/3 domination in the research market, followed curiously enough by the French company, Ethos, European company, then IBM, Fujitsu, and then only the Chinese companies, Lenovo, Shugon, and Inspur. So clearly, the US, European, and Japanese companies produce the big computing system for research installations. If you look at the breakdown in terms of size weighted by size, if we look at the breakdown for the commercial market on the right-hand side, the situation is quite different. It's basically totally inverted, with the 3 Chinese companies producing by far the most system in the top 500, and all the others being rather marginal. So research and commercial market behave very differently, again, in terms of who produces their system. This is now the breakdown for the companies by size of system, by performance share. And you see by size of system, Fujitsu made a big step up, followed then by Cray, HPE, and IBM. While on the right-hand side, if you look in the commercial market, the number of systems installed by the Chinese companies is large enough to even give them an edge up in that market, clearly an edge up in that market. But again, the other companies tend to install larger systems, even in the commercial market, than the Chinese systems. Looking at base technologies, you see the system share here in terms of what systems are using. Intel means it's using an Intel chip as main and only processor, while Intel slash NVIDIA means the system is using an Intel as main processor, but is using a GPU from NVIDIA as an accelerator. So you see both markets are actually dominated by systems without accelerators. Even the research market, that was a surprise for us, followed by systems with various types of accelerators. Clearly, Intel-NVIDIA combination being much more dominant, while the research is on the right-hand side, while on the left-hand side, the research installations, they have a more varied approach to architectures. They are more willing to try out different things. The surprise here, however, was that both markets are still slightly dominated by systems without any acceleration. Looking at size, it changes somewhat, especially for the research market, because accelerators are very important there. And now the biggest slice actually being the ARM processor, which is, of course, again, due to Fugaku and its big impact in terms of performance. But overall, the situation is somewhat similar, with about 1/3 to half of the system not using accelerators, half of the install performance produced by systems without accelerators, and about half to 2/3 of the system of the performance being produced by systems with accelerators. So with that, I'd just like to summarize. I told you Fugaku is the new #1, and that's why our next speaker, Satoshi, is going to give a brief presentation about it. It did measure not only 415 petaflops on the HPL benchmark, but actually over 1 exaflop on a new benchmark called HPL AI in reduced precision. So that's very exciting. That's just as exciting as the other measurement. The top 10 had a very nice turnover. It has 4 new systems now. That is in contrast to actually having a record low turnover for the list itself for various reasons. And the 2 market segments of research systems and commercial systems are actually behaving very differently. And it's interesting to watch that, how it evolves over time. And with that, I like to give back to Horst.
Thank you, Erich. Thank you for an exciting presentation and for bringing not only exciting news, but also a very detailed analysis of the trends of the top 500. With that, it is my great pleasure to move on and introduce Satoshi Matsuoka. Satoshi has been the director of RIKEN CCS, RCCS in Kobe since April 2018. This is the top tier Japanese HPC center that represents all of HPC in Japan. It has been hosting the K computer, and of course now has been developing the Fugaku system that we just heard about it. And it's not just the system, but it is also conducting all the cutting research in HPC in Japan. Satoshi is well known in the HPC community. He was the leader of the Tsubame series of supercomputers at the Tokyo Institute of Technology, where he still holds a professor position. And he continues his research activities in HPC as well as scalable big data and AI. So congratulations, Satoshi. Congratulations, Riken, RCCS, and to the success with the Fugaku system. And please tell us a bit more about this marvelous new system. And again, congratulations to this accomplishment.
Thank you very much, Horst. Do you hear me? Firstly, I'd like to say we're very honored. And I would like to firstly thank the Top 500 organizers for giving us all the awards, all the efforts over the years. I'd like to also, of course, express my thanks to the team at Riken and also our close partner, Fujitsu, with whom we've been developing the machine for the last actually 10 years. And also the ministry, MEXTI, who sponsored us over the years for this enormous project. And of course, the Japanese taxpayers and the HPC community, who basically have supported us in various ways, including their valuable tax money. So Erich has already mentioned some of the traits of Fugaku. I'll just go over a very brief presentation. A lot of detail can be found in Jack's slide, but also we will be presenting these in various other presentations as we go along over the years. So Fugaku has been in the works, like I said, for the past 10 years, in fact. The first inception of the machine was back in 2010, and that was even before the predecessor, the K computer, had been commissioned in production. And even before my current center, RCCS and the predecessor center, EICS, had been built. So it's a very long project. And after various years of preparatory studies, identifying the application needs of the new machine, our intention was never to build a machine that only be good for benchmarks, but really had studied many applications. And we took towards what would be the exascale machine, era machine, that will cater to these very large speedups necessitated by the science. 2014, the project was officially launched. 2018, the first chip, AC Core FX chip, came out of the fab. And 2019, installation started in December. And despite all the COVID situation, there were a lot of challenges, but the team and Fujitsu and Riken pulled through. Installation, all the shipments were done on May 13th, and we're here today. And it's been announced that Fugaku is the new #1 system. And again, this was done in close collaboration with the application community. That we had collaborated even preceding the K days. And it was a co-design effort over the years. And by identifying the 9 important areas that are of high concern to the Japanese taxpayers at large, we have set out to identify the applications and set 9 applications that we had hoped will achieve more than 100 times speed up. And at the same time, we had to value ease of programming because we were expecting to run varieties of applications, not just these, but also applications that will be upcoming, such as those in big data, and now AI and others. So already Erich introduced this, but really we have built a brand new processor. It's an ARM instruction set, but it's a brand new design by Fujitsu and Riken. And basically, in a nutshell, it's a CPU. So it's, it runs the same ARM code as you would on a smartphone. It will run Red Hat Linux out of the box. It'll run Windows, it'll run PowerPoint even. But it's also built to accommodate very large bandwidth to supply its vector units, because our studies showed that bandwidth is very, very important to sustain the speed up of the applications. So the chip was really designed for real-world apps. And later on, we added some AI acceleration features like short precision, reduced precision arithmetic. But again, the chip was designed to really accelerate real-world applications and accommodate wide-ranging sets of HPC applications, both classic ones and the modern ones. And this really shows in the power profile of the performance and power profiles we are running on both Fujitsu and Weekend, where we're seeing up to 3 times or even more both performance and power advantage over existing CPUs. And as Erich alluded to, our power efficiency is pretty much in the range of a GPUs or the latest breeds of accelerators, specialized accelerators, while being a general purpose CPU. And again, 3 times more powerful and also 3 times more power efficient compared to the traditional CPUs. And this was because we really tuned the chip for HPC and not on the generalized, like web workloads. So also, Erich already alluded to the various numbers for the entire system. First to achieve very large flops, exaops, and as a CPU machine, and very, very high bandwidth, more than 163 petabytes per second memory bandwidth. And in some operations, this machine is 3 orders of magnitude faster than K. But to put this in context, compared to normal IT infrastructures, a single Fugaku is about 20 million smartphones, which runs the same code. So think of Fugaku as putting 20 million smartphones in a single room, or equivalently 300,000 servers in a single room, standard servers. And these, by coincidence, are about the same number as the annual shipment of respective units in Japan. So if you had 2 Fugakus, basically, you can pretty much fulfill the so-called edge-to-cloud and compute requirements of the entire country of Japan. And that's the magnitude of the machine we have built. And for the benchmarks, again, it's been introduced, and we had achieved quite a good speed up, and include the benchmark like i500. We haven't measured IO500 yet, but we're seeing consistent multi-factor speed up over previous number 2 machines. So I think we're contributing to healthy speed up of the overall technological advance of the community. And moreover, we haven't really, this is about 70 to 80% of Fugaku's capabilities. So in the future, we may improve the performance of the system. Finally, benchmarks only represent the, benchmarks only represent the facets of the system. The real importance is the real applications. And one of the things we have done is deploy Fugaku almost a year ahead of its scheduled general production to combat COVID-19. And we have two lines of applications. One is medical pharma, where we're studying the power of Fugaku, allowing the study of viruses and the drugs that will be effective. And there we're already seeing 100 times speed up over K compared to what has been achieved on K on this COVID-19 analysis. But also what's been receiving lots of attention is the social, societal, or epidemiological applications, including simulations of droplets aerosol, and also how the viruses, the infections may spread, and how things like contact tracing applications may be effective. The latter is also achieving tremendous attention, and it's been on TV, all over TV last week, and it's really helping to mitigate the virus infections at macro scale. And we hope to collaborate with other countries in the world and regions of the world to fight this crisis that's facing humankind. Again, I thank the organizers, everyone, and hopefully we can help to contribute to the advance of HPC and solve societal problems such as ones in COVID-19. Thank you.
Thank you, Satoshi, and congratulations again on accomplishing this remarkable milestone of half an exaflop of almost HPL performance and exaflop on AI performance. We are going to move on to some questions, and I have received some questions from the audience, and I would like to ask something to you, Satoshi, directly. And one question is here: can the Fugaku system be upgraded to a 64-bit peak of 1 exaflop?
Well, of course, if we have the money, obviously anything is possible. But what we have done really is not, again, not to shoot for peak performance. That is to say, our design metric was basically to accelerate existing K applications by 2 orders of magnitude. And in some sense, the excellence in the very benchmark, not just the LIMPAC top 500, but just across the board, HPCG, HPLAI, Graph 500, and so forth, basically is a result of our efforts to accelerate the applications. So the outcome is applications driving the benchmarks and not the other way around. So, so we're very satisfied with the result. Again, you know, if we make progress, it's only it'll only be because we will have made progress in the application speed up, by which we could be achieving exaflops.
Thank you. I have maybe another question just to follow up also for you, Satoshi. And the question is, has there any attention been paid to make the software ecosystem of Fugaku open source? How can the community profit from the development of new scalable tools?
So that's a great question, because software and the software ecosystem was the priority in the development of Fugaku, was the priority. And that's why we went to the ARM ecosystem from the Spark, which was the K's ecosystem. And that was not very, I would say, proliferating. So firstly, we made a decision to go with ARM, and this has led to a variety of collaborations with various institutions worldwide, and also with ARM company and so forth, with DOE, with the European institutions, and so forth. And also, by the course of this collaboration, we are all these tools simply run out of the box. For example, the Red Hat Linux, which is an open source operating system, with CentOS, it just basically runs out of the box. And we have collaborative efforts with Livermore on SPAC. So we're helping the Livermore folks basically adapt the SPAC package manager to the ARM ecosystem. And this is also collaborating with other parties like Syndia and also some of the European institutions. And a lot of those, majority of those software open source, and they simply run, and it's very easy to tune them to the new system. Yes, so again, software is the key. That's the heart of a computing system, and we're making every effort to enrich the ARM ecosystem so that it'll be one of the dominant systems in the HPC community.
Thank you, Satoshi. There are many more questions on Fugaku, but I'd like to put one question to Jack and then one to Erich. So the one for Jack is, do you expect to have a significant increase of non-x86 systems in the future of the top 500?
Okay, let's see if I can answer that. Looking at Erich's slides, it appears that Intel, the x86 architecture, is found in about 95% of the machines today. Some of those machines have accelerators, and some of those accelerators are from NVIDIA, but 95% today of the top 500 machines use Intel. And that has been going on for a number of years, roughly around that number, 95 or a little bit higher, in fact. I would expect in the future that number to drift down a little bit as we see more machines appear with ARM ARM being the base architecture. But Intel currently has that I'll call stranglehold on high performance computing with over 95% of the machines. Erich, do you want to add anything to that?
So in the past, there were other companies producing main processors, such as IBM with the power architecture, which is still there. AMD, of course, is producing x86 compatible ones. ARM is coming in with Fujitsu starting to sell ARM-based systems, and in the US, we have an ARM-based system at Sandia. So there is a nice innovation. But as we are approaching the end of Moore's law, as a naked performance growth is slowing down the pace of it. The innovation in architectures, being on the chip level or being on the system level, is becoming more and more important. And with that, we have been expecting to see an increasing number of variety of architectures in the top 500 in the market. And it's refreshing to see that actually happens. There is a lot of companies out there trying to build new chips, designing new chips. And we have to see how many of those are going to be in the top 500, are going to measure the HPL or the HPL AI benchmark. So I think we're going to see a large variety, but I also think that, especially for the commercial market, the x86 architecture is going to be by far the dominant one for quite some time.
Okay, thank you, Jack and Erich. So I have the very last question for you, Erich, and the question is, will there be an ISC award to celebrate your retirement? I don't know about this. The real question is, so congratulations on your retirement, but will you still be involved with the top 500?
So yes. Yes, I am retiring from working at Lawrence Berkeley National Labs. I'm going to stay an affiliate to the lab. I will certainly continue the top 500. And the whole point of retiring for me is not to disappear. The whole point of retiring for me is that I'm now going to have a lot more time for my fun projects, top 500 being the foremost of those. So I'm going to be very much around. And
thank you, Erich. So we're looking forward to see you, hopefully also in person at future SC and ISC conferences for top 500 sessions and birds of a feather. And with that, thank you for your many years of contributing to the top 500. I'll turn back to David Keys.